In this screencast, we're going to talk about surface forces and then talk a little bit about the fundamental phase changes. So, our first conversation is about surface forces. We need to introduce some new vocabulary. So the first is what's referred to as viscosity. Now, viscosity is sort of like referred to the liquid flow rate. So as I'm pouring liquid out of a container, think of as I'm pouring oil out of a container, the molecules move kind of slow because they're big and long molecules and they're sort of like falling all over each other. And so some liquids flow slower than others. And as you could imagine, it has to do with these intermolecular sort of forces in and amongst the liquid. So we have these forces that are sort of what are called cohesive forces, that are the attractive forces inside the bulk liquid, if you will, and they're equal sort of in all directions. So it's those intermolecular attractive forces that we've already talked about, the dipole-dipole forces and the London dispersion forces. It's sort of like the magnitude of those forces. So we call this the force of cohesion. Now, on the surface, we've got, we're down here in the bulk, the forces are equal in all directions, but up on the surface, you'll notice that these molecules right there on the actual surface are sort of attracted to the molecules next to them and are attracted to the molecules below them, but there's no molecule sort of on top. And so what this gives rise to is sort of a net force that's pulling these molecules in. These molecules being pulled in all directions on the surface, but there's a net sort of pull down. Now the magnitude of that sort of net surface force, we have a term for it. It's called surface tension, and it's just a measure of the strength of that particular force. And in some species, some liquids have a much greater surface tension than others. Now, one of the consequences of this surface tension has to do with sort of how the liquid interacts with the shape. So we know that liquid in general, if I just have a drop of liquid, it likes to be a sphere in terms of its lowest energy state, in terms of stability in that bulk phase. So we know, like raindrops, example, are spherical. Now, we can talk about the force of cohesion in terms of that the molecules sort of staying together next to them, but then we have this other force which is called is related to adhesion. And cohesion is the molecules sort of like how they're interacting with each other, and adhesion is the molecules interacting with the liquid and the container that they're in. So if the force of adhesion is greater than the force of cohesion, then the liquid is said to wet the container, and water is an example of that. So again, force of adhesion means, the molecules would rather are attracted, the attractive force to the container is greater than the attractive force to each other. In the case of water in a glass tube, that force of adhesion is greater than the force of cohesion. That's why the liquid sort of like goes up and is like the opposite of a sphere. However, if the force of adhesion is less than the force of cohesion, then the liquid sort of acts as a sphere. And so, for example, mercury would rather, the liquid mercury would rather sort of be attracted to itself than to the container. So the meniscus in mercury in glass is actually inverted. So we're now going to talk about the fundamental phase changes. So let us talk about the interaction between a liquid and a gas. And this is mostly for vocabulary more than anything else. So here I have our double-headed reaction arrow. And if our species, smiley face, just any old species, goes from the liquid phase to the gas phase, we call that vaporization. And from the gas phase to the liquid phase, we call that condensation. Now these are the official terms that we're using, and people will sometimes refer to this as boiling, but our technical term is vaporization. The reason why we need a technical term is because we're about to quantify it and do calculations associated with this. So we need to be crystal clear on our language, so we'll use the term vaporization and not boiling. So this phase change obviously requires energy, and so for example, the So water liquid going to water gas. The delta H associated with that, we call that the delta H of vaporization because that's the phase change, is 40.6 kilojoules when the reaction takes place at 100 degrees Celsius, which you know is the normal boiling point of water. Now, the delta H of vaporization of water at 0 degrees Celsius, and it does have a vaporization energy, is actually a little bit different, right? So I want you to note that the delta H of vaporization is sort of temperature dependent. It doesn't change very much, so 40.6 to 45.1 from 100 to 0. So delta H's are, in fact, temperature dependent. This will probably be the number that we use most often because when we're normally going to be talking about water liquid going to water gas at the boiling point of water. Now, it shouldn't be too much of a stretch to understand that delta H of vaporization is always greater than 0. It always has to be endothermic. We always have to put energy in. And the way to remember that is to think about what's happening when we're going from a liquid phase to the gas phase. We're actually breaking apart, if you will, all those intermolecular attractive forces that are holding the liquid molecules together. We're severing them, so we have to put energy in. And we can find tables of delta H's of vaporization. You'll never find a table of a delta H of condensation because if you know what the vaporization energy is, you know what the condensation energy is. So simply because it's just the reverse reaction. So if I wanted to know what is the energy associated with condensing 1 mole of water vapor into water liquid, it's the reverse of their vaporization reaction. Enthalpy of vaporization is always greater than 0. That means enthalpy of condensation is always less than 0 and equal and opposite. So the delta H of condensation of water would be minus 40.6 kilojoules. So that's liquid and gas. We also have the interaction between solid and liquid in those phase changes. And going from liquid to the solid, we refer to that as freezing. And going from solid to liquid, we refer to that as fusion. So going from the solid to liquid, we would also expect, again on the molecular scale, that we are loosening up those intermolecular attractive forces. In the solid, the molecules are held very rigidly, and then when they get to the liquid, they're sort of like held a little bit less tightly. So we would expect this to be endothermic, and in fact it is. So water solid going to water liquid, basically the delta H of fusion, because that's the state change here, solid to liquid, delta H of fusion, is a positive 6.01 kilojoules at 0 degrees Celsius. And for the same reason that delta H of vaporization is always greater than 0, the delta H of fusion is also always greater than 0. And by the same token as before, that condensation and vaporization are equal and opposite, the delta H of freezing and the delta H of fusion are equal and opposite. So you'll never actually, it's very rare that you're never going to see a table of delta H's of freezing because for whatever reason, convention, we publish delta H's of fusion and delta H's of vaporization. We just give numbers for the endothermic phase changes, knowing that we can always calculate what the energy is of the exothermic by reversing it. And then our last, just for semantics, our last set of phase changes are the going from the solid phase to the gas phase, and this is just, again, for semantics. We can go directly from solid to gas or gas to solid. Going from solid to gas is sublimation, and going from gas to solid is deposition. The most common example of sublimation is that of dry ice. Dry ice goes directly from a solid to a gas and never goes through a liquid. That's why it's referred to as dry ice. And so here's sort of like a just sort of review slide, if you will, that sort of helps you remember all those different phase changes and what their language is and what we call each one of them. Okay, so let's talk about sort of like these phase changes in terms of energetics and what we can do with those actual numbers. So this is referred to as a heating curve. Right? So here I have a sample of water at minus 20 degrees Celsius, and sort of on the x-axis we're just sort of like putting total constant energy in and sort of like analyzing what's happening. So down here we have solid ice that's at minus 20 degrees Celsius, and as we add energy to it, the temperature is going to slowly increase. It's just going to absorb that energy until it reaches 0 degrees Celsius, right? And then we're going to have that phase change. So to figure out how much energy is required to go from minus 20 degrees Celsius to 0 degrees Celsius, well, we're just heating something. So if you'll recall from thermodynamics from first semester, we're heating the solid, and so that's simply equal to the specific heat of the solid times the mass of the solid times the delta T of the solid. That's all I need to know to calculate that particular value. So once we reach 0 degrees Celsius and it's all solid, then what we have to do is we have to undergo that phase change. So now it's a phase change where there's no temperature change, right? It's still at 0 degrees Celsius until this is just the melting of the liquid, the melting of the solid. So there is no delta T. To figure out this amount of energy is simply the enthalpy of fusion, the delta H of fusion, times the number of moles. Because remember, delta H of fusion is kilojoules per mole. So we just have to know the number of moles. So when we're calculating this part, notice we need to know the mass and the specific heat of solid and the delta T. The phase changes are a completely different calculation. We need a delta H of fusion, and it's usually per mole. All right, so now we're here, and we've melted all the ice. Now it's just pure liquid. And as we put more energy in, the liquid is going to change temperatures. And so again, it goes back to, oh, okay, I'm heating something and changing its temperature. So in this case, I'm heating the liquid. So I just need to take the specific heat of the liquid, which is different than the specific heat of the solid, times the mass of that liquid, times the delta T. So in this case, to figure that out, if I wanted to go the whole way, I'd have to know, oh, I went from 0 to 100. Then we get up to 100 degrees Celsius. And then we hit another phase change. Now obviously again, the temperature is not going to change until we completely evaporate it, or completely boil it all off. So in this case we're vaporizing the liquid, and so in that case we need to know the delta H of vaporization of the water, and that's in kilojoules per mole. And we want it in kilojoules because we're trying to figure out how much energy was associated in there. So this is in kilojoules per mole multiplied by the moles. Again, there's no mass in here, and there's no delta T because, well, there's no delta T. Then finally we get to a point where we put in enough energy in to boil off all the gas and turn it all into a gas, all the liquid into a gas, and then going from here up to 140, then we're just heating the gas, and again it's just a generic heating. When the amount of energy needed to heat something is equal to the specific heat of that something times the mass of that something times the delta T of that something. So notice that the heating of the gas, the heating of the liquid, and the heating of the solid are very similar. They're just specific heats times mass times delta T. Old school thermodynamics. The only sort of the only new wrinkle that we put in here is figuring out how much energy is associated with doing those phase changes, right? So if we know the delta H of formation, it's in kilojoules per mole, multiplied by moles. If we know the delta H of vaporization, kilojoules per mole, multiplied by moles, that's how much energy is associated. One last thing I want to mention is notice that the amount of energy needed to melt the solid sample is less than the amount of energy needed to boil the sample, to vaporize it. That should make sense if you think about what's happening on the molecular scale. In this case, we're just sort of like loosening those intermolecular forces, but they're still attracted to each other. Whereas when we're going from the liquid phase to the gas phase, we are severing those intermolecular attractive forces and breaking them free such that those individual molecules can fly and be free in various directions. Good luck.